Equilibrium. Okay, this is the last big idea. This is probably the one that most people want to review. We're going to look at most of the conceptual things. If you want calculations, there's going to actually be parts on the slide where it says like review here for calculations. And we can definitely go through on, like, if you find one in class that you want to do, like, we can definitely go through one too. So what is equilibrium? Keep in mind, at the bottom, all of the learning objectives are down here. You can find all of the learning objectives on the class website under After School Review, I think, or if you, AP Review. There's a list of learning objectives. So what is it? Okay, well, it's when your forward and your reverse rate are equal. The reaction does not stop. Okay, the reaction does not stop at equilibrium. It's just forward and reverse are equal. So you're not actually seeing a change because they're happening at the exact same speeds. Net amounts remain constant. You have something like this. Okay, if you're given a graph that really looks like either of these, okay, usually concentration versus time. Remember that you always start with reactants. So your concentration at time 0, you have a lot of reactants, you have no products. Notice that as you make more products, you use up your reactants. And once the concentration stays the same, notice the reaction is still proceeding, but your concentrations aren't changing. That's because you've hit equilibrium. So if they give you a graph like that and it says, you know, at what point do you hit equilibrium? Well, you hit it when the lines plateau. How do you write an equilibrium expression? So KEQ or KC or KP, what's the most general way to write it? Products over reactants. What do you not include? Solids and liquids. Okay, and then obviously if you're doing KP, you're doing everything in pressure. KC, you're doing everything in concentration. Looking at Q versus K. So K is your equilibrium constant. Remember, you can have KC, KP, KSP, KA, KB. But it represents at equilibrium. There's only one time that K changes.
I don't know what that sounds for.
Because teachers can go home. Is it 2:45? Yeah.
That's weird.
It's like, bye teachers. I mean, I left at like 5 o'clock yesterday, so whatever. But, that's okay. I went home and then went to sleep. And then woke up late this morning. Oops. K is at equilibrium. There's only one time when K changes. Temperature. K never changes any other time unless you change temperature. When you're looking at any given time, that's Q. Okay, you can think of Q as reaction progress, the reaction quotient. Q is at any time in the reaction. And then you can compare Q to K, and we'll look at that. Like we said, Q and K only includes gases and aqueous solutions, no solids or liquids because they're pure. We said products over reactants, and then what you're seeing here is how we manipulate Ks. So this is like Hess's law for equilibrium constants. Right? If you square, if you multiply a reaction by 2, right, instead of multiplying K by 2, you square it. What if we need to flip a reaction? Normally, like in delta H or delta G, it would be negative, but you always do to the power. So it's actually be to the -1, which is 1 over. It's the reciprocal. And then if you have to add 2 reactions together, you multiply your Ks. And remember, K is all about multiplying and exponents. So this gives you an example down here. Okay, you have 2 reactions with K1 and K2, but we want to get to this red reaction. Okay, talk to the person next to you and see how we would manipulate, first, how we manipulate the reactions to get this, and then what we would have to do to K, and then see if you guys can figure out what K actually equals. Okay, so what do we have to do to this top one? So we have to divide all of the coefficients by 2. Because we don't want 2 CO2s, we only want 1. So if we divide this by 2, it's essentially multiplying by what? 1/2. So what do we do to the K then? Okay, to the 1/2 power, which is the square root. Okay. Then what do we do to the bottom reaction? Okay, divide it by 2 and flip it. So divide by 2, we flip it, so that means that we're going to be doing 1 over 1.3 e to the negative 10 to the 1/2 power. And then we add these together, we cancel everything out. What do I have to do with my k's now? Multiply them. Right? You should get 2.9. Okay, now be careful how you put it in your calculator. Okay, do 1 over square root of this, solve that. Do square root of this, solve that, and then multiply them together. Now you could be asked questions about this K value now. Okay, what does it mean if K is greater than 1? Products are favored. Right, if K is greater than 1, products are favored. Now it's not very much greater, so you're probably only going to have a small amount of extra products. Okay, so then kinetics and equilibrium. Remember that kinetics looks at speed of reactions, how fast reactions occur, reaction rates. We have rate laws, right? We have rate laws that describe a reaction. Rate equals K times the concentration of your reactants. Your rate constants are always determined experimentally. You always need lab data. Equilibrium describes when our forward and our reverse reactions are equal. So a lot of times you'll see it written as rate of the forward equals rate of the reverse. And we use this a lot when we had our fast step as our first step. We had to set the two equal to get rid of intermediates. If our rates are not equal to start, okay, the faster reaction is going to go more. Okay, the slower reaction is going to try to speed up as much as it can until they equal. The whole point of equilibrium is that your forward rate is going to equal your reverse rate. And then if we disturb somehow, so here we have everything in equilibrium, H2, NH3, and N2. How do we know initially right now that it's at equilibrium, even if it didn't say initial equilibrium? Yeah, they're constant. Your concentrations are constant. The reaction is still going, but your concentrations are constant. And then it says we add more H2, right? It spikes up. Okay, well, we add more H2. What happens then as the reaction keeps going? As it keeps going, what happens to our H2? It gets used up, which tells us more than likely H2 is going to be what? A reactant or a product? Reactant, because it gets used up. What's the other reactant on that graph? The N2 on the bottom, because again it's being used up. And H3 is probably a product because you're making more of it. Right? They could very well ask questions like that where you're just looking at a graph. I think there was one on the multiple choice, something like that. But notice it always goes back to establishing equilibrium. No matter what you do to it, it's going to always go back to equilibrium. Okay, then Q versus K. Okay, Q at any point. So if it says you do another experiment and you add 1 mole of this and 1 mole of this and 5 moles of this, which way is the reaction going to shift? You don't know if it's at equilibrium, so you need to calculate Q, and then you compare it to K, because it lets us know if we need more reactants or more products. You have the bars vertically. Yeah, that's vertically. We did it horizontally, right? We did them like this. However you do it is fine. but when Q is less than K, in order to make it equal, this is nice because it shows the direction that your reaction is going to proceed, right? You're going to make more products in order to get Q equal. If it's less, if Q is equal to K, well, that's easy because it's at equilibrium. Right? If Q is greater than K, these are good lines. Look at those lines. Wow. No. If Q is greater than K, it's going to make more reactants to make them equal. Now, if you're like, no, I don't want to remember that. Just remember what K is. Right? You guys said it's products over reactants. If Q is too big, you have too many products, you need to make more reactants. If Q is too small, you don't have enough products, so you need to make more. Okay, so when you compare Q to K, that helps you know what you need to make more of in order to get back to equilibrium. Okay, calculating K, there's a couple different ways that we can calculate K. You're going to do both. The first way is if they already give you the amounts at equilibrium. That's nice. No ice table. If they already give you amounts at equilibrium, you plug it right into the K expression. Right? So you always want to write your equilibrium expression first because you never know if they're going to give you points for that. So for this example, how would I write the equilibrium expression? And which one would I, well, let's just worry about writing the equilibrium expression first. So how do I write the equilibrium expression for this example? K equals what? CO times what? CO2 and? Now, there's a reason I didn't do anything around this first. Because they gave us moles of each. What else did they give us? The liters. So what are we probably going to be finding to plug in? Concentration. So then what K would this be? C, right. C for concentration. So we'd be finding Kc here because they gave us concentration. So with the person next to you, see if you can solve for the concentration for each, plug it in, and find K.
Yeah, what does she want?
You're going. I'm making you go. You're going.
Remember when she said she'd take us out to dinner and then she felt the liar?
What's probably saying? Just go back.
Okay. So the big thing with this, the big thing with calculating K here is that they gave you the amounts at equilibrium. Every amount that you put into a K expression has to be at equilibrium, not initial. Has to be at equilibrium. So you start by finding the concentration of each, plug them in. Why didn't we have any exponents? None of them had coefficients.
Just as a refresher, what do we do again for when it's not at equilibrium?
Ice table. That's what we're going to do next. Yeah. Okay. So this is how we find K if they give us everything at equilibrium. Now, if they give us initial, we use ice tables. Okay. I always say when in doubt, well, like you guys said, stoik it out. You also could ice it out, I guess. So, yeah. When in doubt, go to moles, stoik it out.
We make money club.
Yeah, they kind of just make them up.
There's a lot of when it goes.
Yeah, they just
sit back there.
yeah, they sit back there and just make up.
Sometimes they sing.
Yeah. Sabrina draws like.
Just a creative.
Yeah.
Sabrina and
Yeah.
Kate fight.
Yeah, Sabrina can fight. That's true. You're the only one representing today.
Yes, I am. Proud of it.
Yeah, because Austin.
Technically, it is.
Technically, Austin is here, but in spirit.
Yeah.
He's probably so mad. He's probably staring at the live thing. It's
Yeah.
not working.
Someone could text him. Okay.
Nah.
We had issues.
Let's let him go.
Okay. Actually. No. Okay. If they give you initial amounts, we have to use an ice table. Okay. So again, always write your equilibrium expression first. Then determine either concentrations or pressures, whatever they give you, and then use an ice table. Plug in the ice table, find your amounts, and then plug it in to K. So this says initially a mixture of 0.1 molar NO, 0.05 molar H2, 0.1 molar H2O was allowed to reach equilibrium. So I'm going to start by writing this out again. Double arrow to H2O. Okay, so initially, what are my amounts? 0.1. Okay, so if they don't give you an amount, assume it's 0, plus it tells you. Okay, so then at equilibrium, NO had a concentration of 0.062. Determine the value of K. Now notice we have coefficients now. So if I did minus, let's say we're just using x's, what would it be for this one? If I was just still using x's, like minus x plus x. Minus 2x minus 2x. Okay, so we're going to plug x's in. Now we could actually find x here. Right? Just make an algebraic expression. Because first, what's 0.1 minus 0.062? 0.038 equals 2x. What's x? 0.019. So that means this is minus 0.038 minus 0.038 plus 0.019 plus 0.038. So 0.05 minus 0.038 is what? Glad you got math in your head. Or using a calculator. So then 0.138. So here are equilibrium concentrations now. Now how do we solve for K?
How did you get those?
So they gave us this 0.062 in the problem. It said, yeah, yes. Now with K here, let's write our K expression. Am I doing Kc or Kp? Kc, because they gave us concentrations. What goes on top? Products. So concentration of N2 times concentration of what? H2O squared, don't forget, over NO squared, H2 squared. Don't forget your squares. Don't be a square and forget your squares. Alright, then you just plug your numbers in. You get your answer. You ever heard of like being a square?
Like a loser.
You're square.
Isn't it like you're boring?
Yeah, it's like you're boring.
You're square.
Don't be a square. You're a square.
Walk away.
So, K is 650. Greater than 1. What's favored? Products. Okay. Then we could calculate equilibrium concentrations if we're given K. So it's just going backwards. Right, we have K. It's when we plug in X's. What do we have to do if we have X's? Assume X is small. Assuming is good in this case. Again, you can see the steps. Write the expression. Set up your ice table. Determine the changes using X. And then you're going to have, 0.1 minus X, 0.1 plus X. Still products over reactants. And then you can just solve for concentrations or solve for pressures. Okay. I'm just going to move on so we get done with stuff. Okay, magnitude of K. We've kind of been talking about this as we've been going through. This shows our particle diagrams. If K is small, okay, less than 1, can K be negative? No. Okay, it's always greater than 0, but it's less than 1, so it's tiny, tiny numbers. If K is less than 1, you have mostly reactants. If it's equal to 1, you have equal reactants and equal products. And if it's greater than 1, you're going to have more products. Now, if it's like much, much, much greater than 1, you're going to have almost all products. The reaction's going to pretty much go to completion. And so this is how they would use particle diagrams to ask you, what would you say is the value for K? Which of the following would be the closest value for K? Oh. There's a freeze. Le Chatelier's principle. Now, with Le Chatelier's principle, there is an animation on this PowerPoint. Remember, this is online. This actually shows in a lab, and it's like a virtual lab almost, where you can actually adjust concentrations and pressure and temperature, and you actually see the color changes. And so I would recommend taking a look at that. But with Le Chatelier's principle, the biggest thing with Le Chatelier's principle is you have to be looking at something that is already at equilibrium. If it is not at equilibrium, you cannot use Le Chatelier's principle. You have to be at equilibrium. You have to make some disruption to equilibrium. And so this shows you how adding or removing something, changing pressure or temperature can shift your reaction. Really, there's three main things you look at: concentration, pressure, temperature. Because concentration is like adding a product or removing a product or reactant. And then with temperature, think about heat as either a product or a reactant. If it's endothermic, what side is heat going to be on? The left, the reactant side. Yep. Okay, so this is what I'm talking about with the lab. This is where that animation comes in, because you can actually examine equilibrium using Le Chatelier's principle in the lab. You guys did a lab, I think, with iron thiocyanate, but you guys did it with colorimetry because it changes colors. But what you can do is, if you change the amounts, it's going to change color as it shifts to equilibrium. So it might become more yellow if you're making more iron. It could become more orange if you're making more of the iron thiocyanate ion. So you can actually use just qualitative observations to look at Le Chatelier's principle. And then when we look at changing Q versus K, you can have some changes that are going to affect Q. The only thing that affects K is temperature, right? K only changes when temperature changes. Everything else is just affecting Q because it's still going to get back to equilibrium because your K is the same. Okay, and then we shift to acid base. Acid-base particle diagrams. This learning objective specifically says students can generate or use a particulate representation, that's a particle diagram, of an acid and base to explain what you have more of at equilibrium. So what that's saying is, in this particle diagram, for example, you have H3O plus, you have, let's say, A minus, and then These are all just waters. Okay, so what you have most of is actually H plus and A minus. Now, they're going to make it look a little bit different because it's like, what about all these things back here? They'll make it look a little bit different than this, but if you have mostly H plus and A minus, that means that your acid has ionized into its ions. It's a strong acid. The more ions you have, the stronger the acid. Versus the weak acid, okay, here's HA. Notice here's a molecule, 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 molecule. You have a lot of acid molecules. That means it didn't break up into its ions. So that's going to be a weaker acid. So like HCl versus acetic acid. HCl is going to look more like this, where you have all these Cl minuses and all these H pluses. And over here, for acetic acid, maybe you have one H plus and one acetate ion, and the rest are just acid molecules. Okay, so big question off of this that I would ask is, can you look at a particle diagram and tell whether something is a strong acid or a weak acid, or maybe a strong base versus a weak base? All right, the more ions you have, the stronger the acid or the base. The more molecules you have, the weaker it is. Okay, so then this kind of goes right with that particle diagram, looking at the pH of a weak or strong acid. Notice the pH of 3. Okay, if you have a pH of 3, what is this solution? Okay, it's going to be acidic. Somehow it's going to be acidic. Don't let little things like that slip out of your brain. Like pH below 7 is acidic. pH above 7 is basic. But notice here you have all these A minuses and H3O pluses. You don't really see any HA. This is probably a strong acid. Versus over here, okay, you see a lot more HAs. Just because the pH is the same, okay, when you look at the particle diagram, that's really where you're going to tell. You can have a pH of 3 and it be a strong acid and a pH of 3 being a weak acid. What you look for is how much it ionizes. All right, remember, weak acids ionize only like 5%. Because what this means is you probably started out with your concentration being very different. Okay, pH, you need H plus to find. What else with the strong versus weak? I think that's really it. 100% for strong acids, 5% for weak. So weak acids ionize much, 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 much less. Okay, then titrations. Lots of titration curves. This says, see the source link to review calculations. I will tell you, I was kind of writing some stuff down. Remember, strong acid, strong base titrations is all stoic. There's no equilibrium involved with strong, because it goes to completion. Right? All strong acid and strong base calculations, those go to completion. You're not even going to have a double arrow, because all you're doing is taking H plus OH minus and making water. The strong weak titrations, that's where you start with neutralization. Right? You're neutralizing whatever's being added, and then you do equilibrium. So you do stoic, and then you do an ice table. Some things with titrations. If we have, let's use this right here. Right, this says buffer region. Buffer region is only in a strong, weak titration. You don't have a buffer region in strong. Right? Notice in this strong curve, there's no actual curve. It just kind of goes flat, up, flat. But in a strong weak, you have this buffer region. At half, so equivalence point is 40. At half, this is where pH equals pKa. That's why your half equivalence point is so useful. Your pH equals your pKa in the buffer region. In order for pH to equal pKa, your weak acid and its conjugate are equal, the concentrations. Because if you remember the equation that we used, was H plus equals Ka times weak acid over weak base. This was the buffer equation that we used every time. Well, in order for this to equal this, which means pH equals pKa, these have to be equal. That's at the half equivalence point. And then pH at the equivalence point, remember, strong always wins. So if it's a strong base, it's going to be above 7. If it's a strong acid, it's going to be below 7. Let's see. And then the only other thing with a polyprotic, just meaning more than one proton, essentially every titration curve that you see is for one H. So we start, here's an equivalence point where it spikes, then we go more, and then it spikes again. So this probably tells us that we have 2 H's. Okay, the more you have, the more H's that you would have. Okay, and then KW and temperature. So the biggest thing with KW is you can only use it at 25 degrees Celsius. As temperature changes, people always find this hard to believe, but as temperature changes, the pH of water actually changes. So if you are at a temperature of 50 degrees Celsius, then neutral is no longer 7, it's 6.63. That's why when you guys are always in my room and you're finding the pH of water, it's never exactly 7. Because let's be real, my room is not 25 degrees Celsius. Today it's probably 30. Which is why it's not exactly 7. People are like, oh my gosh, Miss Carney, your water's not 7. Well, that's because KW changes. Any calculations that you're going to be required to do with KW, it's going to be at 25. They're not going to ask you to calculate KW if it's, 75 degrees Celsius. Instead, it's just important to know that it does change. K is an equilibrium constant. It does change with temperature. Okay, so then here's a question with acid base. 25 milliliter sample of HF. Okay, as you read through, label. What's HF? Hydrofluoric acid. What kind of acid? Weak acid. Right? Label as you go through. It's titrated with 25 milliliters of 0.30 molar sodium hydroxide. What's sodium hydroxide? Strong base. So we have weak acid, strong base. At the equivalence point, what would the pH be and justify with a reaction? So first, what would we expect the pH to be? Right? Greater than 7. Why? Strong winds, right? So that's what we say. We say strong winds, but let's actually see why. We have NaOH plus HF. What's the double replacement reaction that would happen? NaF, H2O. NaF is a salt. Is it neutral? No. Which of the ions is not neutral? Why is Na plus neutral? It comes from a strong base. But when we have F minus in water, right, because that's what we have right now, F minus in water, what is F minus going to act as? Conjugate base. So what's it going to do from the water? Oops, HF makes OH minus. That's why F minus is a base. Makes OH minus in solution. Right, so your answer is going to be C, and the reaction that you would use would be this. F minus is a conjugate base. So when it's in the water, it's actually going to hydrolyze and make OH minus. That's why F minus is a conjugate base. That's why it acts as a base in solution. Okay, vinegar is 0.5 molar acetic acid with a Ka of 1.8 times 10 to the negative fifth. You might not remember it, but you use that Ka a whole lot. What would be the pH of the solution? We've done these in class. What are you going to need to use if you have Ka and you're trying to find pH? What are we going to have to find eventually? H plus. I have to erase my nice. I'm going to leave this. Okay, so always write any reaction that you can, write it out. So acetic acid is HC2H3O2. It's going to ionize partially into what? H plus and C2H3O2 minus. Okay, what is anything initially that we have? Yeah, vinegar is 0.50 molar. We don't have any products. So, do we know the change? X. Minus X, what about these? Because now these are our equilibrium amounts. And what else are we given? Ka. So 1.8 times 10 to the negative fifth. What do I need to do, though, to make this easier? Assume X is small. Or you can say X is much less than 0.50. So then we have X squared over 0.50. You solve for X. What is X? In terms of like H plus. And then how do I find pH? Negative log of H plus. All right, so this is just using ice table. Kind of hard to read up there. But we write out our ice table. We always ignore water. So if it says something is dissolved in water, it's not reacting with water. You don't really even need to include it. If it says you have a solution in water, you don't have to include it. Unless it specifically says, like, it's hydrolyzing. Hydrolyzing is when you have to include water, if water is acting as an acid or a base. So then, after you go through everything, you get a pH equal to 2.5. Does that make sense? Does it make sense that, yeah, why? It's an acid, right? It's less than 7. And then number 2 says identify and compare relative strengths of the 2 acids and the 2 bases. So look at these, OH minus, NH4 plus, H2O, and NH3. Let's first label on each side what's the acid and what's the base. So OH minus and NH4 plus goes to H2O and NH3. What is OH minus? It's a base. Because to go from this side to this side, it accepts a proton. So if this is a base, what does that make NH4 plus? Acid. And then over here, if this is the base, what does that make water? It's conjugate acid. And NH3, you know, is a base. Now let's compare them. Typically, you could use the Kas to compare. The higher the Ka, the stronger the acid. The higher the Kb, the stronger the base. But we can just kind of use what we know. OH minus versus NH3. Which is the stronger base? OH minus. Because all of the strong bases that you know are hydroxides. So OH minus, even without knowing Kas and Kbs, just use what you know. OH minus is a strong base. NH3, you have to know that's a base, that's a weak base. So if OH minus is the stronger base, what does that make water? The weaker acid. Remember, if you have a really, really strong base, its acid, its conjugate acid, is basically neutral. That's why when we look at salts, right, we say if it's, Na plus is neutral because it comes from a strong base. Just like that, if you have a strong base, its conjugate acid is neutral. So if this is the stronger base, when you compare acids, its conjugate is going to be the weaker acid. NH3 and NH4 plus, though, this is the weaker base. That makes NH4 plus the stronger acid. So just remember that the stronger in the pair, okay, if one is the strongest, the other one, its conjugate, is going to be the weakest. Okay, so then again, looking at titration curves. Okay, looking at titration curves, if you have a particle diagram, okay, you can kind of look what you have in the particle diagram based on where you're at on the titration curve. Initially, you're going to have all acid, okay, because you have all acid. In the buffer region, that's where you have, for the most part, equal amounts of acid and its conjugate, because any base that is being added is being neutralized. Okay, so any base that's added is going to be neutralized, so you're going to make the conjugates. At the equivalence point, moles are equal. Right? Moles are equal at the equivalence point. Moles acid equal moles base. And then all the way up at the top, that's when you have excess base. All your acid is gone. And then buffers. Oh, buffers. Biggest thing with buffer. Right, remember pH equals pKa. So when you want to find a buffer, let's say that has a pH of 4, you want to find the pair that has a pKa closest to 4. When you make a buffer, what's like the main way that you make a buffer? Yeah, usually you have a weak acid or a weak base, and it's salt, right? You want a weak acid and a weak base, or a weak acid or weak base, and its conjugate, and the conjugate comes from the salt. The other ways that you can make it are in the lab, in this buffer region, right? If you have like a strong acid and excess weak base, you always want more of the weak in the buffer. That's another way that you can make it in the lab. But typically we see it made with a weak acid or base and its conjugate, which comes in the form of a salt. With the buffer, this equation is the one that we use. H plus equals Ka times weak acid over weak base. Every time. Doesn't matter if you have a weak base buffer, a weak acid buffer, this is what you want to use. It's just easier for you to remember. Okay, because then that makes it easier for you to calculate pH. The pH of a buffer, like I said, is determined by the pKa. When both species, Ethan's not here again, have equal concentrations, this is equal. This is equal to 1. pH equals pKa. That's why pH equals pKa at the half equivalence point. And then you just want the pair that has a pKa closest to the pH. In terms of buffering capacity, if you want a very high buffer capacity, you want very high concentrations. Okay, the higher the concentration, the more it can buffer, because a buffer is only effective as long as you have conjugate acid-base pair, as long as it can react. Once you run out of it, it's not going to work anymore. So you want very high concentrations in order to have a high buffer capacity. I don't know why they keep doing that. Okay, so this says we have a sample of acetic acid. It's titrated to the half equivalence point. Okay, again, I'm going to find some key things. So acetic acid, half equivalence point. What do we know about the half equivalence point? Okay, pH equals pKa. So it's titrated with NaOH. Which of the following options shows the correct ranking of the molarities of the species in solution? Then it gives us the pKa. Okay, so talk to the people around you and see which ones you think are right. Which one? There's only one.
Think about it. Hey, they're nice-ish. Take it to the point.
equivalence point, why does pH equal pKa? These are equal. Your weak acid and the conjugate are equal. Which of these has your weak acid and your conjugate equal? B. Okay, that's going to be the right answer. And then you do have some H plus in solution because this does ionize a small amount. OH minus is going to be the least concentration because at the half equivalence point, you still have buffer that's neutralizing any added base. Okay, so then the way that a buffer works, and I know we've talked about this, the reason that you need a buffer or an acid-base component of a buffer is because you want to be able to neutralize any added acid or base. The whole point of a buffer is to resist pH change. And so if you add, let's see, this is HF and NaF. Right? What is the acidic portion of this buffer? HF. What's the basic part? F minus. So if we add base, the acid part of the buffer is going to neutralize the base. So HF plus OH minus, we're going to make F minus and H2O. So we make more of the F minus, but that's okay because we haven't changed the pH. If we add acid, the F minus is going to react with the acid to make more HF. That's the whole point of a buffer, is to not change the pH very much. Okay, then Ksp. What does the SP stand for? Solubility product. Okay, Ksp is the solubility product constant. Some terms to look for that tell you you're going to deal with Ksp. If it says that a solid is dissolved in water, you're probably going to use Ksp. If they give you the Ksp value, which they have to if you have to use it, if they give you the Ksp, then you're going to be using Ksp. It's at equilibrium. K is equilibrium. If you see Ksp, you're going to have a double arrow. If it says saturated solution, that's Ksp. So looking at this, it says what's the maximum number of moles of AgBr that will fully dissolve in 1 liter of water if the Ksp value of silver bromide is 4 times 10 to the negative 12. Start by writing your reaction. I have AgBr. That's a solid. If they give me Ksp, what arrow should I use? Double arrow. K is equilibrium. You don't need water. Okay. Don't include water. Just show the solid at equilibrium with its ions. What are the ions that make up AgBr? Okay, don't forget your charges. That's usually one thing that a lot of people miss points on, is they just forget their charges. Okay, so what's the maximum number of moles that will fully dissolve? So now, I just want the Ksp expression. So we don't even need to put numbers in yet, just the expression. How do I write an equilibrium constant expression? Products over reactants. But the reactant is a solid. You never include solids. So it's just going to be Ag plus times Br minus. Okay, now, let's just say this is at equilibrium. We don't worry about solids. You start with 0, and then it's plus what? X. Why is it just x and x? Why not like 2x? Coefficients are 1. So let's just plug this and this into the equilibrium expression. All right, so 4 times 10 to the negative 12 equals what? X squared. Okay, then you solve for x. Well, let's see, square root, so 2 times 10 to the negative 6, right? 12 times 1/2, yeah. Great, that's X. Now this says moles. Why can this just be my answer? It's 1 liter. Yeah, it's 1 liter. Now this right here, this molarity, this is, you'll see it called molar solubility. Molar solubility is still moles per liter, but this is typically, you could think of it as a concentration for solids. If this is a 1-to-1 ratio, you could say the molar solubility of AgBr is also 2 times 10 to the negative 6. That's how many moles you can dissolve in 1 liter of solution. Okay, so then here's another one. One where you're using data, which is something that they're starting to incorporate more. The use of data. So using a conductivity meter and a pH probe, a student determined the molar solubility, see, keyword, molar solubility tells you Ksp, of a saturated solution, ding ding, saturated solution, Ksp, made by dissolving hydroxide salts in water. Student's data is shown in the table below. Which of the hydroxide salts has the smallest Ksp? Now, here's a question. What does it mean to have a very small Ksp? Doesn't dissolve very much, because think about what Ksp is. It's how many ions you make. You don't make very many ions, the small Ksp. The smaller the Ksp, the less it dissolves. The higher the Ksp, the more it dissolves. So what you need to do for this is, based on this, I'll show you how we could do this one. Barium hydroxide will be at equilibrium with its ions. What are the ions that make this up? Ba2 plus, 2OH minus. This is 0.11. Use coefficients to find the solubility of the ions. So what's the solubility of Ba2 plus? What about this? How do I find Ksp now? Now be careful with this. How would I write the Ksp for this right here? Concentration of Ba2 plus OH minus squared. Okay, don't forget that. So you're going to take 0.11 times 0.22 squared. Find your Ksp. You're going to do that for each one to find your Ksps. This would probably be a free response question because you wouldn't be expected to have to do that for all of these. Okay, so now I'll show you the answer. Just keep in mind, this is what you would do. The biggest thing people miss is forgetting the squares. Right? Write your Ksp expression first. Okay. So then just a couple more things and then we'll be done. Common ion. Okay, remember that common ion is just adding something more to the initial row. Right? Common ion is just the way that you can add or remove solubility. Okay? Kind of like Le Chatelier's principle because you're at equilibrium. Dissolving a solid, so salt dissolution. Remember that breaking bonds is endothermic, forming bonds is exothermic. Breaking intermolecular forces is also endothermic. So this shows you right here. Separating solvent and solute molecules is endothermic. Okay? When you bring them together and make a solution, typically it's exothermic. Typically. You have seen some that's been endothermic. And what that means is, if it's endothermic, separating the molecules takes way more energy than you get out when you bring them together. Now, no matter what, bringing things together is always exothermic, right? Almost like forming a bond. If you're forming an attraction, you have positives and negatives coming together, that's exothermic. The overall process is going to be based on how much energy it takes to separate and how much you get back when you bring them together to form a solution. Entropy, when you make a solution, you're increasing disorder. Entropy is going to increase when you make a solution. Typically because you have a solid which is like very, very, very ordered. And then you're making this solution. And then this is a lot of stuff. Just to tell you that you can compare delta G to K in order to determine if something is thermodynamically favorable. That's the term they use now. It's spontaneous. But thermodynamically favorable, if you see that on a free response, that just means spontaneous. And so when you make a solution, if your delta G is negative, it's not spontaneous. No, other way. Did I say negative? Delta G is negative, it is spontaneous. If delta G is positive, it's not spontaneous. My nose keeps rubbing. And so you can actually calculate and determine if you have a spontaneous reaction. You have something that's exothermic and increases disorder. That's spontaneous. Just brings us back to that chart, knowing at what temperature everything is spontaneous, or if it ever is. Right? If it's endothermic and you increase order, it's never spontaneous.